see. Let's pick up. I think we were doing Newton's proof. Yeah, so we had this idea that the potential energy, and we'll see some questions later about this, but the potential energy is equal to this minus g mm over r. So if I have a mass m here, and I have a mass m here, and I hold them a certain distance apart, a certain distance r, they have potential for motion, right? That if I hold them apart like this, if I were to let them go, they would fly together because masses are attracted to one another. And if you were to somehow let yourselves go in your chairs, you would just all suck up together because there is a force that's attracting you. All right, that's the gravitational force. So it's equal to this minus g mm over r. So Newton's proof then, he said that the work, and we've seen this before, but work is F dot, I'm going to call it F dot R, the distance that they travel. And he further said that if I want to know the total amount of work, I sum up this. I say that the sum of this is going to be F dot dr, as r goes from big R to infinity. And remember, F dot R, F dot dr, these are vectors, that this is equal to F dr cosine of the angle phi between them. So let's just remember the dot product, right, that we had last semester. The dot product we use to find the product of two vectors that are in the same direction. And so that's where that cosine of phi term comes from, that if I have F in this direction and R in this direction, and then they're separated by that angle phi, then F R cosine phi is going to be the component of the first vector that's in the same direction as the second vector. Y'all remember the dot product? That was in contrast to the cross product, which we're going to use both of those this semester. But the dot product takes two vectors and takes the component of one that's in the same direction as the other. And we saw that last semester and when we looked at work, because to find work, the force had to be in the same direction as the displacement. And that's what Newton's saying here, that our work is the dot product of F and the distance that it over which F acts. We'll see that again soon. So we're going to see the dot product again later. We'll see the cross product quite a bit as well this semester. So I know that F, which Newton had found, is equal to g m over r squared. And because those vectors are in the same direction as one another, that phi is equal to, well, let's look at this. I have a force that's in this direction and a force in this direction. The angle phi between F and R is going to be 180 degrees. All right? So I can do this integral, and the work becomes the integral from R to infinity of minus gmm over r squared dr. Where did the negative come from here? Where did I get this negative? I want to venture a educated guess. Okay, that's a good guess, but that's not it. Mathematically, where does it come from? Like, look at the integral that I'm doing. I'm doing the integral of this f dot dr, which simplifies to f dr cosine phi. I have an expression for f. I have an expression for phi. So where do I get this negative here?
Cosine of 180.
Right, the cosine of 180. So that's where that negative comes from, just mathematically. And then if I do this integral, I get the expression that we've already seen, which is the integral of 1 over r squared dr, which is just 1 over r. So my work then is equal to minus g m over r. And this is equal to my potential energy. By the work energy theorem that we saw last semester, if I do work on an object, I increase its potential energy. So I have this object, I move it up in this direction, I've increased its potential energy by the amount of work that I've done. Alrighty, we'll see that come up. A couple of other little notes. Since the force is conservative, that means that the energy is path dependent. Or excuse me, not path dependent, path independent. We talked about this last semester, where if you move up, if you walk up a mountain, if you walk straight up the mountain, or if you take a circuitous path up the mountain, your gravitational energy is changed by the same amount. It's path independent because we're dealing with a conservative force. Not all forces are conservative. What's a type of force that's non-conservative? That actually loses energy. The frictional force is non-conservative. Contact forces are non-conservative. All right, so some forces are conservative, like the gravitational force. Okay, let's see. Let's do a few clicker questions. I think you just double check. I think we can do this. So a satellite orbits the Earth with constant speed at height above the surface of the Earth equal to the Earth's radius. The magnitude of the satellite's acceleration is which of these? So I have the surface of the Earth, the radius of the Earth, another radius of the Earth up is where the satellite is. What is the satellite's acceleration? The magnitude of the satellite's acceleration. Is it a quarter, a half? Is it the same as the acceleration due to gravity on Earth? Is it twice or is it 4 times that acceleration? So if it's on the surface of the Earth, it has this value. If it's 1 radius above the Earth, what is the acceleration due to gravity at that point? All right, feel free to ask your neighbor. Y'all are sort of split on what the answer is, but feel free to ask your neighbor. You look back at your notes or whatever. We did talk about how do we determine the acceleration due to gravity last time. I'm going to stop in about 5 seconds. Okay, before I show you the answer, let me remind you that we said that F equals mg, and that F between 2 objects on the surface of the Earth is going to be g, mass of the Earth, mass of the object, over r squared. And since the m's cancel here and here, that would be like the mass of an object. Then we get this expression for the acceleration due to gravity, which is gm over r squared. And so what we've done here is we say that at the surface of the Earth, this is the Earth right here, at the surface of the Earth right here, your acceleration is not q, it's g, and that's at some radius r. So now I want to know up here, what is your acceleration due to gravity, and now I'm at 2r. Let's ask you this again and see what you put. You were split. Before you were split between either 1 or 2, or A or B, a quarter or a half. Rethink your answer. Ask your neighbor what they put maybe. If I double r, what happens to the acceleration? You are correct that it is going to get smaller. The acceleration due to gravity at higher altitudes is less than what it is at the surface, so that's good. But think about how it changes. I'm going to stop at 37. Just 2 more seconds. Okay, that's good. A is the right answer there. I notice here, let's see, y'all were split, so A is the right answer there. It's an inverse square relationship, right? That if I double R, then it changes it by a factor of 4 because it's squared. So G is going to decrease by a factor of 4 or by 1/4. It's 1/4 its original. All right, let's see. I think is that joke worthy? 86%. Where does, and remember, tell jokes, you don't spew out the punchline if you happen to know it. You just say, I don't know, where does a one-legged lady work? Where? At IHOP. But One day I think I might have a one-legged lady in my class. I don't think any of you ladies are one-legged, and then I don't think I can tell that joke. Is that inappropriate to tell that joke? Some of you might know a one-legged lady. I'm sure that some of you do. So if you're offended, I'm sorry. Bye the joke. Okay. This figure shows a binary star system. The mass of star 2 is twice the mass of star 1. Compared to the force F1 on 2, what is the magnitude of F2 on 1? So compared to the force of, this is back, compared to the force here, how big is the force here? You follow me? How much bigger or smaller is this force compared to the force that's acting on this object? How much bigger or smaller is this force compared to the force that acts on that one? Is this force smaller? So, 1 or 2? Is it bigger, 3 or 4? Or is it the same, that would be 5, as the force that acts on this object? Feel free to ask your neighbor. This is our gravitational force. This is sort of one of Newton's big breakthroughs. We talked about it last semester and again this semester. I'm going to stop at 138. Y'all are still a bunch of Aristotelian thinkers, right? Because you think that the bigger mass feels a bigger force. And people often think that if you have a big object and a small object and they interact with one another, then the bigger object feels a bigger force. But we know that's not true, right? That if we have a big object and a small object and they interact with one another through a force, whether they come into contact or whether they just touch, they're exerting forces through gravity or electric fields or whatever, they're going to feel exactly the same force. And that is a demonstration of which of Newton's laws, the first, second, or third? It's okay to say the wrong answer. The third law, right. So this idea that for every force, I have an equal and opposite force. So what is the right answer here? E. No, it's A. No, it's E. It is E. Okay. They have the same force acting on them. We saw this in Newton's universal law of gravitation too. G m over r squared. Notice that it has both masses in it. Each mass, we would use the same expression to calculate the force as it's applied to that mass. Now we'll do this one, then we'll move on. Planet has 4 times the mass of the Earth, but the acceleration due to gravity on the planet's surface is the same as on the Earth's surface. So the planet's radius must be what compared to the radius of Earth? It's more massive by a factor of 4, but the acceleration due to gravity is the same as that on Earth. So what's up with this planet? Okay, you need to rethink your answer because you're not putting the right answer, most of you, so far. Think about what are the relationships, the mathematical relationships between the acceleration due to gravity, that's that g, and the mass and the radius. We derived that. We set mg equal to g mm over r squared. And we got an expression for g, little g. If I quadruple the mass, I want to keep g the same value, 9.8 or whatever. What do I have to do to the radius? Okay, that's a lot better. I'm going to stop at 130. 130. Okay, better. Many of you would put what answer? Do you know? D is right, but before, many of you would put what? No, you put E. A lot of you, maybe you would put A, but a lot of you would put E, which is also wrong. It's okay, Emma. Uh, so remember our value for G is big G. Remember that's just a constant times the mass of the planet divided by r squared. So if I increase this by a factor of 4, in order to get this to remain constant, I have to have half the radius. So if you make the mass of the Earth 4 times bigger, then to keep the same acceleration due to gravity, you'd have to make it half as small. The radius half as small. Oh, excuse me, twice as big. Y'all follow me? Yes. There's a 2 in there somewhere. All right, let's stop there. We'll come back to it. Let's look at escape speed. Have y'all seen, what was that movie where they cussed a lot? The Mars thing where the guy got, y'all see that movie? Huh? The Martian, yeah. It was a good movie. Like, people at NASA, I've worked with people at NASA, they don't cuss like that. Like, it blew me away. It was a good movie. Like, I'm not offended by bad language, but scientists, they don't walk around dropping the F-bomb every other word. Do y'all know that? Do your chemistry faculty, do they talk like that? Dr. Dow, does he talk like that? Dr. Gianna Moore? Dr. Wayman? Maybe Dr. Wayman. Like something else. But scientists don't talk like that. Anyway. But they talk about how he gets off the planet. And he has to get enough speed to get off the planet. You remember? Y'all seen the movie? Read the book or whatever? That's called the escape speed. And they talk about in that movie the escape speed. The escape speed is actually pretty simple to derive. And so, Matt Damon, right? That was the guy. He can calculate. I think he wasn't, what was he? He was like a biologist or something. Huh? Botany, right. So it's pretty easy to determine the escape speed that you need. It's not really dependent on much. I mean, there is some air resistance that you might need to consider, but largely it's just you need the energy to escape the gravitational field of the Earth or of whatever planet you're on. So by the conservation of energy, which we saw last semester that is that the total energy is conserved. So E tot is always the same in a closed system. And you can think about what is your closed system. You might have two particles interacting. There's no energy going in or out, so that's a closed system. Or you might have a larger system like, I don't know, the planet Earth, which is also a closed system largely. But anyway, by the conservation of energy, one can find the speed required for a projectile to leave the object's gravitational field. And this is what he did on that movie, and that's what you could do if you ever find yourself stranded on Mars or some other planet all by yourself, and you need to find out how fast do I need to go to get off of this planet. It could be you one day, so just be prepared here. So we say that U plus K is equal to 0. We sort of start with that idea. And what I'm saying there is that when a projectile reaches an infinite height, it's not really going to infinity, but when it gets so far away from the planet that it's trying to escape from, that it's like the planet doesn't even really have any hold on it anymore. When a projectile reaches an infinite height, let's put that in quotations, because it's an approximation, that both U, that's the gravitational potential energy, and K, that's the kinetic energy, are equal to 0. That the sum of those are equal to 0. That I don't have any more gravitational energy, that it's all been transferred to kinetic. So I have my potential energy of my two-particle system. That's Gm over the radius. We just derived that from Newton's law. plus my kinetic energy. See, what is the kinetic energy? I always forget it. Do y'all remember? Oh, yeah, it's 1/2 mv squared. And that's equal to 0. This velocity, this is our escape velocity. It's the velocity that's required for you to escape the gravitational field of the Earth. And so the escape velocity, if I just solve it for escape velocity, as Matt Damon did, it's 2g m over r, where m is the mass of the planet, and r is the radius of the planet. So make sure that you know the mass of Mars and the radius of Mars if you go there. Listen, on the test, you might have some short answer stuff. You might have some questions. You have all these equations, so don't bother memorizing them. But you might have some questions, just sort of short answer type questions, where I ask you, what is the shell theorem? Describe to me the shell theorem in your own words. And the shell theorem, you know, is that if I have this shell of matter and an object outside of the shell looks like it's a point mass. And so Newton's universal law of gravitation applies. Or I might say, you know, in your own words, how would you derive the escape speed? And you would say, well, it's where the energy of the object, the total energy, goes to 0, and I set my gravitational potential energy equal to my kinetic energy. So be prepared for that, more of that to come. Like, I'll sort of give you more guidelines as we get closer to the exam, which is not that far away. When is the exam? Does anybody know right off the top of their head? Somebody look, it's on the back cover of your workbook. February 6th. So this is the 20th. That's about, what, a little more, about 3 weeks or so. So the exam's not that far away, and it's probably going to cover Chapter 0, Chapter 1, and then Chapter 1.5, and maybe even getting into Chapter 2. But probably just those first 3 chapters. Alrighty. You should be looking at your homework, too, at this point, because you should be able to do a good fraction of your homework at this point. Numbers 1 and 2 and 3 and 4 and 5. You should be able to do most of your homework at this point. All right, let's look at something a little bit different now. Sorry, let me let this think. While I was thinking, let's do a few more questions. Okay, rank in order from the largest to the smallest the absolute values of G, that's the U, that's the gravitational potential energy, for each of these pairs of masses. And these numbers, you know, you have 2 and 2 here, 4 here, they give the relative masses of the objects in the relative. And by the way, these are in the back of your workbook, so if you want to follow along in the back of your workbook, these should be there. Isn't that right? Yeah, so they are in the back. So rank these. Which of these statements describe their gravitational potential energy? All right, let's try to wrap it up in about 10 seconds. Stop at 1:30. Feel free to ask your neighbor. I'll go on to 1:35. Just guess if you're not sure. All right, we're sort of over the board. I'm not sure what the answer is, but look, I can sort of put this off to the side. On these questions, I like to give these types of questions, these ranking questions. It's not just me, it's other standardized tests and what have you. But I want to start here with my expression for U. I know that's G M over R. I actually have a negative there, but I'm looking for the magnitude, so I can leave off the negative. And then I have the relative masses and the separations of these. Now, if they're close together, that gives me a big U. If I have big masses, that also gives me a big U. But, you know, here like I have big masses that are far apart. So I need to think about how does this affect my U, my gravitational potential energy. I'm just going to do mm over r for each one. So for example, here part E, it's 4 times 4 over 8. So that's 16 over 8. That's equal to 2, right? And then I can do the same for all the others. Here I have 1 times 4 over 4. That's 4 over 4. That's 1. Here I have 1 times 1 over 2. That's 1/2. Here I have 1 times 1 over 1. And that's 1. And here I have 2 times 2 over 4. That's 1. So looks like E has the biggest, D, B, and A have the next biggest, and then C has the smallest. I think that's what most of you put. That is option 1, or A. So now notice I could do the forces, and the forces would be a little bit different, right? Let's see how the forces would rank. How are the forces compared to M and R? Do y'all recall what the expression for force is? Is G over R squared, right? So I could do a similar thing with the forces. Here I would have 16 over 64, which is, what is that? Yeah, 1 over 4. So notice that the force here is you know, smaller perhaps. Let's look at these others. Here I have 4 over 16, which is 1 over 4. Here I have 1 over 4. Here I have 1 over 1. And here I have 4 over 16, which is 1/4. So if I was ranking the forces, this would have the biggest force, and then all the others would have smaller forces. Why does this one have the bigger force? Little bitty particles. Why do they have such a big force? They're close together. I have an inverse square law, and so the inverse square law, that 1 over r squared dependence, drives very much so the relative sizes of the forces. So be prepared to rank things like that on the multiple choice part of the exam. You'll probably have one like that, and it's just good practice. Standardized tests, they sort of like those sorts of things. All right, let's try the next one. The gravitational force between two objects separated by a distance r is which of these? If you're uncertain, ask your neighbor. I want everybody to get this one right. Although a few of you have an incorrect answer. How does F proportional to R, or M, or G? All right, we're going to stop at 50, 50. You know, some of this is just sort of knowing the language, but my gravitational force is Gmm over r squared. So the gravitational force is proportional to, is not m1 plus m2. Notice I multiply the masses, nor is it this. It's not r. That would look like, you know, F equals GMMR. So it's not that. It's not 1 over R, because that would look like GMM over R. So it's not that. So it has to be 3. So this is the right expression, and that's how we describe that in words. That I have this inverse square law, this inverse square relationship between F and R, or F and R squared. So 3 is the right answer, C. Did I mark that correct? Okay, yeah, C is right. Bless you. All right. The value of G at the height of the space shuttle's orbit. We'll stop at 43. Okay, good. C is right. Remember, because G is equal to Gm over R squared, we derived that. We said that mg is equal to Gmm over R squared, and just solve it for little g. This is sort of what we call our gravitational acceleration, the acceleration that you would experience due to the gravitational field. Now, in the space shuttle, how do they accelerate due to gravity when they're orbiting? They don't accelerate at all. They don't experience the same acceleration downward as we do, because, as Jesse said, that the orbit, when the space shuttle is in orbit, is constantly falling. And so if you're falling towards the planet Earth, you don't feel it either. Like you feel weightless as well. So that's something different than what we before called A sub g, which is the acceleration of free fall that we feel. This is the acceleration due to gravity that is due to the gravitational field. We're going to define field soon. All right. I'll post those online. All right, this is still thinking. Okay, I think I got it now. Okay, so gravitational fields and equal potential surfaces. Listen, you've probably never dealt with fields. We're going to deal with fields quite a bit in this chapter and the next chapter. We're going to see fields both with gravity and with electric fields. If you're in the lab and you've already had the lab, then you've already got some introduction to fields. But fields can sometimes be difficult for students to understand. But I just want to encourage you that fields are actually not that complicated. That once you see the basics of either electric or gravitational fields, you'll say, oh, a field, that's just a force per some unit charge. For gravitational fields, the field is the force per unit mass. For electric fields, it's the force per unit charge. So a field gives a force per some unit. So it gives the force per some unit. In fact, my wife, she likes to call them force fields, right? Because they describe a force that something will feel. In the case of gravitational fields, that unit is going to be mass. So the gravitational field gives the force per unit mass. In the next chapter, we're going to see the electric field, which will give the force per unit charge. Okay? So we're going to have forces, and then we're going to have fields, which are a force per unit mass in this case, or sometimes a force per unit charge in electricity. We're going to use field lines and something we call equipotential lines to describe the field. So let's say that we have a mass. We'll say that it's the Earth. I want some way to describe the force that particles feel when they're close to the Earth. So let's say that I have some mass right here, at some point above the Earth. In what direction does it feel a force? It's going to feel a force in the downward direction. What if I have a particle over here? Will it also feel a force in the downward direction? What's that? Okay, but as we're looking at it, it's going to be to the, what's that, to your right. Is that right? Yeah, to your, whatever. It's going to be towards the Earth. All right, and then if I have a mass over here, it's going to look like that. A mass over here looks like that. Now I can draw field lines that come out of the Earth that will describe this force that particles feel. It's really just something that we make up. All right, the field isn't something that you can go out and scoop up in a cup. Right? It's not some ether that's out in space. It's just really a way that we use to describe the force that particles of mass feel. We just made it up because it's helpful for us to describe the force that particles feel. Now, the direction of the arrows give the direction of G. And G, which we've called our acceleration due to gravity, now we're going to call it our field, because that's really what it is. In fact, if you remember where G came from, we said that F was equal to mg, that the gravitational force that an object feels is mg. Watch this. G is equal to force per unit mass. Right? A field is just a force per unit mass. We've been doing this all along, that our gravitational field, we've been calling it G, is force per unit mass. So the arrows give the direction of G. Hey, let me ask you a question. Where is G bigger? Is G, oh, I've already turned your clickers off, so you just sort of yell it out. Or take a moment and think about it. Where is G bigger? At point A or point B? Just think for a second. Where is the acceleration due to gravity bigger? At point A or at point B? All right, now everybody can say it.
B.
Point B, right. Jesse? Is that sign language or B? Really? Oh, that's what you do. That's good. We should get like a sign, somebody to sign during class. Do we need that? Wouldn't that be cool if we did? That would be neat. I've never had anybody that's like me. Okay, gosh. That just blew my mind. That would be, I don't know how they would do that. Okay, so anyway, the arrows give the direction of G. We said that the acceleration due to gravity is bigger here. Notice that the field lines, they're closer together here. And so while the arrows give the direction of G, the density of the lines give the magnitude of G. All right, so notice here, the lines are just closer together. Out here, they're farther apart. We'll express this in vector form later, and we'll deal with fields quite a bit in this chapter and the next chapter, and sort of coming chapter. But these are field lines. You had a lab. You're going to have two labs on them, actually. The arrows give the direction of the field. The density of the lines give the magnitude. So where those lines are more closely packed, then that's where they it's bigger. Okay? Gauss's law. Before we get into Gauss's law, I just wanted to define some things. Flux. Gravitational flux in particular is probably something you've never used before, the concept of flux, and we're going to use it a couple times this semester. Flux is equal to G, the value of G, times the surface area through which G travels. So if we go back up here and we imagine that there is some surface here through which those field lines travel through, G represents the field lines. This is the surface. If I just take the product of G and the surface through which G is going, that gives me what we call the flux. Mathematically, we describe this. The flux is phi, and it's equal to the integral of G dot N dA. N is a unit vector. That means it has a value of what? Unit vectors have a value of, like I, J, and K, they're unit vectors too. They have a magnitude of 1, right? So they're only used to show direction. They're not used to show any magnitude or measurement, only direction. So N is a unit vector. I'm going to draw it with a hat, actually. Let's draw it with a hat here too. So that's just usually how we do it. It has a value of 1, and it has a direction that's perpendicular to the surface. All right? So imagine that I have a gravitational field that goes from your left to your right. I have all these field lines that are traveling from left to right. All right, they're parallel to one another, and they're going in this direction. And this is my surface. They're traveling through this surface. So if they travel through this surface like this, my value for G dot N would be equal to G, because hold on. Give me just a second, y'all. Let me check this. Yes, okay, yeah. So, sorry, I was getting off track. So N, remember, is a unit vector that's what? Perpendicular or parallel to the surface? Perpendicular. So I have this vector N that is perpendicular to the surface. What is the direction of the field lines? In this case, in this imaginary world that we're doing. They're in this direction, right? So what is the value then of G dot N? If my vector N is in this direction, and my vector G is also in this direction, what is the value of G dot N? Okay, it's positive, yeah, that's good. Well, N has a magnitude of 1, right? G has a magnitude of G, whatever it is. They're in the same direction, those two vectors, and so the dot product is going to be G, right? So if my vector N, and my vector G are in the same direction, then my value for the flux is going to be G. Now what if I flip this surface like this? I still have my vectors G going in this direction, but now my vector N is in that direction. What is the value of G dot N in this case? It's what? It's 0. Why is it 0? Because the dot product, right, takes the product of two vectors that are in the same or opposite direction? Same direction. Right, so when I flip this vector in this direction, now I have two perpendicular vectors, and that dot product is 0. Follow me on that? It's sort of important, because we're going to deal with Gaussian surfaces soon, and this idea becomes very important. All right, so we're going to sort of put that on the back burner, and we'll come back to that, and I'll show you how it's applied for gravitational fields. But let me show you Gauss's law first. Gauss's law, this is on your equation sheet. It says that the flux, this is the flux, that it's equal to negative 4 pi g, that's our gravitational constant, times the mass inside a surface. And don't worry about what the surface is. I'm going to show you that next time. But the Gauss's law says that their flux is equal to 4 pi g times n. So the flux, remember, is g times our area. And I'm going to assume that these two are perpendicular to one another because that's our dot product. Our g and our n are in the same direction, so our area is perpendicular to g, is going to be equal to negative 4 pi g times mass of the inside surface, mass inside the surface. Let me show you one of these, and these are in your homework as well, how this applies. Well, we just have a couple minutes left. We'll just eject right here. I'll pick up with Gauss's law next time for these three surfaces. But y'all have a great weekend doing whatever it is that you're doing, even if it's nothing, okay? I'll see you on Monday morning.